All right, hello Ling 341, welcome back. Today we are going to talk about trills. And before I get into that though, I have a couple of fun links that I want to show you, just kind of follow up on what we've talked about in the two previous lectures on place of articulation and airstream mechanisms. So first of all, I have a link here, not that one, but this one that is a guess the word game. So what this is going to show us, and I'll walk you through a couple of examples, is I don't think I mentioned this in class before, but after the X-ray videos of the early 20th century, and after they realized that if you just shoot an X-ray machine at somebody's face for a long time, they'll probably get sick, they developed a technology called X-ray microbeam technology, where they would instead of like shooting an X-ray at a whole person's head, at a person's whole head, they would put little pellets on top of their tongue or in certain spots of their palate too, I think, that would say deflect X-rays that were projected at their head in a tiny little beam, a microbeam. So they could have this sort of like X-ray kind of zipping back and forth at a very high rate as a person was speaking. And then when they would speak, the pellets would move on their articulators, and they'd get a record of like sort of how the different pellets had deflected the X-ray microbeam in space over time. So they could get some sense that way of how people were actually using their tongues or lips or what have you when they were speaking. And this was popular in the early 1990s, and I guess they also don't use this anymore. They thought that with a microbeam of X-rays, they wouldn't have as much of a radiation risk, but apparently there's still enough there that it's not considered safe technology. But it was done at the University of Wisconsin in Madison, and it's pretty cool. And I'll show you how cool it is by playing a couple of these trials of the game, or rounds of the game, I guess you could say. So like I said, you get sort of point-by-point representation of where a speaker's palate is, where their tongue is, where their jaw is, and also where their lips are as they're speaking. I think this is supposed to be the back of the throat or the pharynx in that spot. So the front of the speaker's face is over here on the right-hand side of the screen, and you're supposed to just guess that out of these four options, what word is this person trying to say, or what word is this person actually saying, rather. So yeah, well, what are they saying? Are sense, wax, almost, or across? And looking at it, I might be tempted to say across, because we kind of have a back closure here, and then looks like an S there. Not much going on with the lips. So when you guess, it tells you what the word is by playing it.
Across.
Yeah, cool. And then you can sync it to see how it looks in real time.
Across.
Which is a lot faster.
Across.
Let's try another
Across.
one. We'll do maybe 2 or 3 here. Yep. Yeah. Looking at the lips, I always forget to look at the lips because the tongue is like so dramatic. But maybe it's a moment.
Moment.
Yeah.
Moment. Moment.
Yeah, I'll
Moment.
do one more. I haven't embarrassed myself yet. Gotta keep going until I do. Yeah, this might be never. Like there's a little lip motion here in the middle of it.
Never.
Yeah. Okay, 3 for 3. I'm gonna quit while I'm ahead, but you can play with this game if you want. It's kind of a good way to review places of articulation and also see how speech actually works, or something like it in a real-time representation. I also have a video which I typically play in class, and I'll play for you now, from a singer named Miriam Makeba. And she kind of speaks for herself, but she was a native speaker of a click language and became famous for incorporating clicks into her songs. This is from about 40 years ago, about 1980 or so. I grabbed it from the internet as usual. It's got Dutch subtitles, so I don't know if this is from sort of Afrikaans speaking South African TV, but either way, you can just watch it and see how she sings.
This next song is also a South African song. It's a Xhosa wedding song.
It claps just for making it quick.
Everywhere we go, people often ask me, how do you make that noise? It used to offend me because it isn't a noise, it's my language. came to understand that they didn't understand that Xhosa is my language and it's a written language. We use the same Roman alphabet in writing it. The only difference is that we pronounce certain letters differently, such as the letter Q, we pronounce no. And the letter X, we pronounce mwa. The letter C, mwi, and the letter R, ha. We have words like U, QHO, 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 Utokoko, which means the Adam's apple. IQANDA, Panda, which means an egg. IXOXO, Itoko, which means a frog. Now, I'm sure everyone here knows that we in South Africa are still colonized. The colonizers of my country call this song the click song, simply because they find it rather difficult saying "Upangachwa."
Yeah, so that's kind of cool. I won't play through the whole song, but I will go back and I'll just play when she says the clicks like in isolation like this. She nasalizes them, right? No. She has kind of an N on top of what, or an engma on top of the click itself. Like that. Okay, so that's kind of fun. I will mention one other thing about clicks, which I should have mentioned last time, but didn't. But when you are trying to produce clicks, if you get stuck on them or have a hard time, one thing you should remember is that they are velaric ingressive sounds. So air is traveling into your mouth as you say them. So you got to think in terms of, sucking air into your mouth as you produce them. Or you can maybe think of, I'm just going to put my tongue up onto the roof of my mouth and then suck it down from there. And you get that sort of click sound. You're like sucking air into your mouth, not trying to push it out. Just keep that in mind for your production exercises, and hopefully they will go well enough. And like I said, though, other than that, I'm going to talk about trills, which involve different aerodynamic mechanisms. In fact, these are kind of interesting because they wind up being cyclical. Okay, so aerodynamic method number one that we talked about is stops. And this is pretty straightforward. So we talked about this process, but you can start airflow coming up out of your lungs. We take advantage of Boyle's law to do this. We compress the volume of our lungs a bit, which increases the air pressure inside of our lungs. And then air will naturally flow from high to low pressure out of our lungs into our mouth and into the great big world beyond that. But inside of our mouth, before the air gets out into the great big world, we can stop the airflow by bringing two articulators together. Like say we bring our lips together, like that. Then the air will be stopped behind that. And then when we release it, it'll kind of pop out. And when we do that, we just kind of relax the articulators. It's not really an explosion. You're not really like pushing through the articulators to get them to pop apart. You just lower your jaw in the case of like a bilabial stop, and then any air pressure differences that exist, if there's more air pressure inside your mouth than outside of your mouth, then air will kind of just travel through that former closure and give you a little bit of what's called a release burst. It's a little kind of pop of air, like the popping of the balloon of the stop closure that you had made. And I think I had uploaded this. Hopefully it's still here. Yep. So there's some examples of this that you can hear and even see in Prot when listening to those Bengali transcription exercises, the sound files for those exercises. So this is
tat,
number 6.
tat,
And especially at the tail end here, this is a nice example here where she's lowering her tongue.
tat,
That little, that's a release burst.
tat,
And if you just try to say that by itself, you'll probably make it sort of like an ejective because you probably hold your breath as you produce it.
tat,
But that just a little bit, this is not really an ejective. It's just a release burst of that final stop.
tat,
So this is just one case where you wouldn't transcribe that with that sort of unreleased or inaudible release diacritic, that little bracket on top of the critic, on top of the segment. And you wouldn't also transcribe it with aspiration either. It's just the stop by itself, and it has a audible release burst at the tail end.
Tat.
Like that. Okay, that's all that's going on there. There's no aspiration. There's nothing else besides the burst of the stop closure. Okay, like I said, though, that's kind of the simplest method, the simplest aerodynamic method that we have in our toolkit. I'm going to give you another one. So this one, instead of saying like ba and just having one stop, I'm going to say like that. And normally in class, I ask, what kind of sound is this? And normally people answer pretty quickly because the title of this lecture is Trills. And so therefore, we're going to talk a little bit about trills. And what I made was a bilabial trill. The voiced bilabial trill has this symbol here. It looks like a capital B, but it's a little bit smaller. Yeah, and so I should put voiced here as well. The voiceless version would just have that voiceless diacritic underneath it because as far as I know, there's no language which has a voiceless bilabial trill. They're possible, they're just not nearly as likely as voiced ones. Oops, didn't get my D in there. All right, so I've got some examples of this from a couple of languages which are spoken in the South Pacific, in a place called the island of Manus, which is north of New Guinea. So this is kind of fun. The two languages are called Kele and Titan. And so these examples have what look like, or they're transcribed as pre-nasalized bilabial trills at the beginning of these two forms. And then these are transcribed as regular stops, but they kind of sound like trills as well. So you can listen to them. And as usual, you can try to sing along at home. These are fun. Do
Bruenke. Bruenke.
Buenke,
Pulim.
Pulim. You might find these also a little bit challenging to kind of put in this context. It's easy to do, right? Like babies do that all the time. It's a little more challenging to put them in a stream of speech, but I think you can get there without too much difficulty.
Boulay.
Boulay,
Boutuke.
Boutuke. Yeah, that's fun. And that's how you would transcribe it if anybody around you were to say that. One question I have for you, though, is how fast do you think this is happening? And normally what I do in class is to get somebody to come up and record this. I don't have that option at the moment, so I'm going to do it myself. My wife kind of wisely declined the opportunity. She's a little too dignified for this sort of fun. So I will, again, embarrass myself by putting myself through the trial. All right, so here we go. I'm going to record myself just making a voice bilabial trill. Actually, I'll make it a voiceless one. That might be easier. And the trick with this is always to make sure you don't spit on your computer screen, and I think I passed that test. But let's move this over to the prop window. And if we look at this, when we open up our editor, we can see two representations. We're not going to talk about this one yet. It's called the spectrogram, but this is the waveform, which we have talked about before. And what we see is change in air pressure over time. At least I believe we talked about waveforms, but if we haven't, that's what it represents. This is air pressure changing over time. And you can see in this representation that we have these big spikes. And those big spikes are sort of like the release bursts of my lips, but they operate in a different way. They're when my lips pop open at any one time. But I'm blowing my lips open in this case, like pushing air through them rather than just like opening up my jaw so you get a tiny little release burst. And the question I wanted to pose is how often do you think this happens? How often do the lips open and close? And so I normally take guesses from the class, and you can guess right now whatever you think it might be. You can put it in the chat window if we're watching this as a group. But the way I'm going to calculate this, and I guess I should have, maybe I can open up my calculator. How about that? Yeah. So I'm going to record sort of 5 cycles of this. So we can see how long the cycle of trilling, in this case, takes by measuring the amount of time between lip openings. So I'll start here and say this is the completion of one cycle to the next big pop, the second cycle, the third cycle, the fourth cycle, the fifth cycle. So it takes us this long to get through 5 repetitions of that. So it's about 0.197 seconds to do 5 repetitions. We can kind of round that off and say we're going to do 5 repetitions in 0.2 seconds or we're going to do 5 repetitions in about 1/5 of a second. I really should have brought my whiteboard here, and I think I might actually go down and get it. So I'm going to pause actually. All right, I thought better of using my whiteboard. I did go and get it. Here you can see it, 5 reps in 1/5 of a second. That's what we got. But I didn't want to have to force you guys to read my handwriting. We'll save that for later. And I'll try to write this out instead on a Microsoft Word document or maybe Excel. But we've got 5 repetitions in 1/5 of a second. And normally when we talk about like the rate at which something is occurring, we want to try to specify how often it happens in 1 second using a unit called hertz. I'll say more about that in a second. But let's try to sort of normalize this to put it on a level playing field and talk about how many repetitions can we get within 1 second. So let's just think about it. First off with saying, well, if I talk about 1/5 of a second, how many fifths of a second can I fit into a second? I can fit 5, right? So there are 5/5 of a second in a second. And that means that whatever value I get out of this, I can multiply it by 5 to say that's how many repetitions I'll get in a whole second, right? If there are 5 reps in 1/5 of a second, then I get 5 times 5 equals 25 repetitions in a whole second, right? So one way to represent that, or one unit to use, would be an old-fashioned term called cycles per second, or CPS. So I get 25 repetitions per second. That's what it means. And a way to say that using a fancier unit is hertz. 25 cycles per second equals 25 hertz. This is a less clear term to use, but it's the one that is more commonly used, and we'll use it throughout this class. So that's what it means. Hertz is cycles per second. And in this particular case, how often are my lips trilling, or how often are my lips opening and closing? They're opening and closing 25 times per second. And what's kind of funny about this is that this works this way for basically everybody. Everybody, when you do a bilabial trill, the frequency of that happening, the lips opening and closing, is probably going to be about 25 seconds, or 25 hertz, sorry, with a little bit of leeway on either side of that. Oh, right. So I'll go back to this point as well, too. But there's a difference between period and frequency. So this, if I'm talking about hertz, that is a measure of frequency. So 25 hertz is the frequency with which my lips open and close when I'm making a bilabial trill. If I want to talk about period, period is 1 over the frequency. So when I'm basically, how long does it take to go through one cycle? Period is how long does it take to complete one cycle. And there's a simple formula for that. Period equals 1 over the frequency. So in this case, period will be 1 over 25, or 1/25 of a second. We don't normally use that term. If you want to think of it in terms of decimals, then you can say it's 0.04 seconds. And I'll confirm that. It should be roughly what we're estimating it to be, but I'll go from one spike of this to the next. I think we started with this one, and I'll go to that guy next to it, and it's a little bit less than 0.04 seconds, right? So that's the period. How long does it take to go from one lip opening and to the next? How long does it take to complete that cycle? Yeah, so this is period. We'll put it in caps, and we'll come back to that notion in a minute or two. Okay, hopefully that all makes sense, and you can be thankful that I didn't have to use the whiteboard for that, so you can read it. But I do have another question for you. Actually, a couple of questions. Number one, do you close and relax your lips each time like they open and close when you're doing bilabial trills? You do if you're making like a ba, like ba, 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 ba. You have to move your jaw up and down pretty quickly to do that. But with, you're not really, getting your jaw involved in terms of moving up and down, or you're not really doing that much with your lips either, right? You're just pushing the air through them. So the question is, like, when you blow the lips apart with the stream of air, why don't they stay apart? You're forcing them open with a stream of air. Boom. What brings them back in. Are you trying to bring them back in? Not really. What's happening instead is that aerodynamics are taking control of the situation. So this is a phenomenon which is known as the Bernoulli Effect, and it's named after this guy, Daniel Bernoulli, who, if I'm not mistaken, was Swiss, and he was sort of a polymath. He dabbled in a lot of different fields, including like physics and mathematics, and actually came from a family of scientists. He particularly lived in the 18th century. His family like preceded him in the 17th with a variety of different accomplishments. And the story I heard about Daniel Bernoulli, aside from what he found out about the Bernoulli effect, is that he and his father at some point entered like some sort of science fair contest, and the judges were so impressed by their work that they gave them like a joint first place award that they both tied for the best, presentation in the contest. And his dad apparently was so annoyed by having to tie with his son that he just stopped speaking to his son ever after that. And they kind of just didn't talk again. Okay, some people are competitive a little too much. Daniel Bernoulli is the Bernoulli we remember. We only remember his dad for that bad episode. And the reason why we remember Daniel Bernoulli is that he came up with this insight into how aerodynamics works. So he found out that in a flowing stream of particles, the pressure exerted by the particles is inversely proportional to their velocity. So we're going to come up with another equation here, which looks a little bit like Boyle's law, but is different. So remember Boyle's law, we have a closed chamber of air, like in our mouth or in a balloon or in a bellows or something like that. And then if we change the volume, that will change the pressure. So decreased volume equals increased pressure, increased volume equals decreased pressure within that chamber by itself. The difference here is for the Bernoulli effect, we're dealing with a flowing stream of particles. So air like flowing through the vocal tract, right? Or maybe like in a canal channel in the middle of a city or something like that, water flowing through a canal or something. We're going to focus on this just for speech though. So we have like a flowing stream of air particles going through our mouths. And then kind of the way to think about this is, I will draw this out actually using my whiteboard, and hopefully I have some different colored whiteboard markers here. But we have a flowing stream of particles like this, going through the mouth or what have you. And if they're flowing relatively quickly, like in this case, then you get not much pressure pushing to the outside. So I just need to find a different color for pressure. Hopefully my brown one works. Yeah. So I get a little bit of pressure pushing to the outsides because most of the streams are just like focused on moving forward, right? Let's say I have a slower moving stream of particles. We'll put it up here. So I'll represent that with shorter arrows moving in this direction. Then this stream of particles is going to exert more pressure to the outsides. So we get bigger push to the outsides. Maybe not even big enough there. Yeah, like that. So in this case, less forward motion or less velocity in that direction, you get more pressure to the outsides. When it's going through really fast, then you get very little pressure going to the outsides. That's the sort of core insight into the Bernoulli effect. So the higher the velocity, the lower the pressure pushing to the outside. There's a trade-off relationship there as well. But again, it's with a flowing stream of particles rather than a chamber of air. And the question is, well, why do we care about this for what we're doing when we're making trills? Well, there's a lot of examples of how this works in the physical world. It's kind of fun to think about. The classic example which is given for this is an airplane wing. And I have since found out after giving this demonstration or example for many years in this class that is a little bit bogus apparently. So try not to take this too seriously, but the idea is you have an airplane wing which is shaped like this. So it's a bit curved on the top and it's basically flat on the bottom. So let's say you're pushing an airplane through the air, as one does. You're moving it forward with a motor in the body of the airplane itself, so the wing comes along with it. And let's say you're pushing through air, and air kind of has to go from this end to the far end. Basically, it has to kind of start at this place and get to this place at the same time, whether it's going on the top or the bottom. And because it has further to go on the top, it's got to move a little more quickly than it does on the bottom. Basically, there's kind of like a vacuum that sucks it there. Sort of like sucking your tongue down in your mouth when you make a click. But in this particular case, because the air has a little bit further to go on top, it's got to move a little bit more quickly than it does on the bottom. So because it's moving more quickly, there's less pressure it's exerting on the top than on the bottom. So that's what this smaller arrow represents. And basically, the airplane wing kind of gets sucked up into the less pressure above it, and it kind of gets helped by more pressure pushing up from the bottom. Like I said, it's apparently more complicated than that, and there are a few other principles in play. But one example which apparently is legit and does work for that is a frisbee, and hopefully you can see that all right. It's my old frisbee team. But there's a curve on the top, right? So again, if you're throwing a frisbee through the air, it's got a little further to go on top than it does on the bottom, which has this little ridge on it anyways. But we'll ignore that for the time being. It basically has a flat sort of direction to go. Shortest distance between 2 points is a straight line, right? So it's shorter here, a little bit longer here. The frisbee kind of gets sucked up into the air when you throw it. And normally when I do this in class, I like to throw the frisbee with a student just for kicks, to throw it both right side up and then also upside down. Maybe you have a sense that if you've ever thrown a frisbee upside down, it doesn't really work as well as when you throw it right side up. There's kind of a bit of a tendency for it to be unstable and maybe get sucked down more towards the ground when you throw it upside down. It just doesn't work as well unless you really practice with it. Okay, so that's a frisbee. It works according to the Bernoulli effect. Another case of this in real life, which you may be familiar with, is your shower curtain. And this is kind of a funny thing. So if you have just a loose shower curtain, not one of those like hard glass partitions, but you can get in the shower sometimes and turn on the water, and then all of a sudden, for some weird reason, like the shower curtain starts like creeping up around you, and you're like, stop it. And you have to like push it back a number of times, and you're like, why is this happening? And the reason it's happening is because of the Bernoulli effect. So if you think about it, like outside of the shower in your bathroom, like air is just static. It's not really doing anything. But then when you turn on the shower, the water is going to move around the air in there a little bit and get things flowing. And because there's more velocity inside the sort of bathtub area, there's less air pressure sort of pushing out from there. So the shower curtain gets sucked into that lower air pressure. It's going to move from the higher pressure air to the lower pressure. And unfortunately, you're in the lower pressure zone, so it gets stuck around you or in your way, or, leaves you feeling chilly or whatever. So that's kind of funny, but real. The struggle is real. I've got some other examples as well of how you can get this to work with pieces of paper. So we'll see if I can make this work in the video. But let's say I have this piece of paper, and I'm just going to kind of try to hold it loosely in front of me here. And what I'm going to do is I'm going to blow across the top, hopefully in this flat line direction as I can. And then what do you think is going to happen? I'm trying not to blow into the paper as much as I can. It's a little tricky. But hopefully you can see that the paper is kind of getting sucked up into that flow of air, right? So as air goes over top of it, it's decreasing the air pressure on top of the paper, and then kind of counterintuitively, the air gets sucked up into it. Now, if I were to blow, hold it like this and blow on the bottom side, then I am blowing directly into the paper itself. So it just pushes it out of the way. So kind of two different effects there, depending on whether you're above or below. So what I'm going to do, I've got two pieces of paper, and I'll see if I can get this to work as well. I'm going to put one on top of the other and then try to blow through the middle of these two. And then what do you think is going to happen? If you want to do this at home and leave these a little bit offset, it usually works a little bit better that way, so I can find that gap. But here we go. Yeah, hopefully you notice that effect. I'm going to actually try to record this. I haven't done this for a while. We'll see if I can make an audio recording. And of course, now it doesn't work as well. There we go. Yep. So I got a little bit of trilling there, right? I got a repetitive pattern where the two pieces of paper, first of all, I blow them apart from each other, and then they get sucked back in. And then that pattern would keep repeating and make kind of a loud, repetitive noise. And since I thankfully recorded this, we should be able to look at it a little bit acoustically. I don't know. Yeah, it's a little bit too noisy. What is this? This is me talking. So I got a little bit of trilling. Yeah, never mind. So we don't get quite as nice structure there as we do with the bilabial trills, but you can hear that sound. Hopefully your ears haven't died yet. Yeah, and you could maybe see it on the video as well. That's basically a trill. That's basically what's going on when you bring, say, two articulators together like your lips and try to blow through them. The airflow will pop them apart. Quit while you're ahead, Steve. The airflow will pop them apart, and then as soon as they're apart, air flows through, and then that decreases the pressure and brings them back together again because there's so little air pressure in the middle. And the exact same thing happens with bilabial trills. So I'm going to walk you guys through this little schematics, series of schematics that I put together just to help you visualize it again in a slightly more primitive way. But let's say this is your vocal tract. This is the inside of your mouth. You bring your two lips together with a certain amount of force. So you do have to push them together to get it started, right? Like that. And this is the outside of your mouth. So I've got this labeled as F sub AD, adductive force, the bringing together force on your lips. And then what I do is that I want to get air flowing from the inside of my mouth out. So I decrease the volume of my lungs. Air pressure increases inside of my body. It stays the same outside of my body because I can't change the air pressure in the whole world in my room or wherever. And because we have this pressure differential, such that pressure is higher inside of my mouth than it is out, air is going to want to flow from the high pressure here to the lower pressure outside of the mouth. So that's what I've got there. And this is going to exert a force against the lips to try to kind of force them open. Eventually it will succeed if you keep increasing the pressure here. And if you're not holding your lips tight or too tightly closed. So air will pop out towards the outside from high to low pressure. And then there'll be a minor sort of change in air pressure in these two parts of the world, a little bit of a lowering in pressure inside your mouth, a little bit of a raising of pressure outside of your mouth. But most importantly, the pressure in this little spot, in this narrow channel where the air is flowing through, will drop dramatically. So because air is flowing so quickly through here, then this air pressure goes down a lot. And I'm already still kind of holding these together a little bit with this adductive force. So I've got two forces kind of pushing these two lips back together again, and eventually they get there. The sort of adductive force overwhelms, and the lowering of the air pressure inside because of the Bernoulli effect. This overwhelms the airflow coming from inside my body, and they get sucked back together again. You're not really pushing them back together. You kind of ideally holding this force constant. It's not that much of a force anyways. What really brings together the lips is that drop in air pressure due to the Bernoulli effect. Your lips get sucked back together again. Okay, and then once they're closed, we repeat the whole cycle, right? So as long as I'm still compressing the air in my lungs, the air pressure inside of my body is going to increase, and then it'll try to pop open the lips again, and then get to the outside and repeat the whole cycle, making a noise each time it pops open the lips to give us that trilling effect, basically. So we'll get, when we look on the outside of our mouths, we'll get this pattern where we see these kind of spikes of air molecules just popping out into the world around us. When we record that in prod or in some computer or machine, we'll see those big spikes of molecules getting pushed as the air pops out from the mouth and opens up the lips in a bilabial trill. Okay, hopefully that makes sense. I went through it a little fast, knowing that you can review it again if you want to in this video. So assuming that you've got it, I'll move on. If you haven't got it, feel free to watch it again, just like repeating the cycle when you do a trill. It should look the same the second time around, or the third time too. Okay, we have other trills, as you're probably aware. So we don't just have bilabial trills in language. There are also alveolar trills. I think I've referred to these once or twice. Famously, they're in a language like Spanish. I'm going to give you some examples from these languages, Kele and Teton again, from the island of Manus. So they have trills in initial position. These are also transcribed as being pre-nasalized, so you can try to nasalize on top of making these guys. Just give it your best shot.
Ruin, Rikei,
Truin,
Rikei,
Treke,
Rili,
Trli,
Rekein,
Trakein. So I'm going to play these one more time, but I will mention that normally, like in a production exercise, if I ask you to make like a bilabial trill, like most people don't find that difficult. A lot of people find alveolar trills like this challenging to make. And I guess the advice I would give you if you're trying to learn how to produce them is to remember that you don't have to force it, as it were. You're kind of trying to set things up so that the airflow can do all the work for you, and you just have to kind of like get out of the way of the airflow or put the right things in the way of the airflow. And it's not something you're doing sort of like with your muscles so much. So a way to kind of try to get yourself in the right position for that, and I'll sort of turn to the side here, is that you want to bring the tip of your tongue up to the roof of your mouth, the alveolar ridge, at the time that you're going to start the trill. And then you kind of want to just blow through that closure. Like with your lips, both your lips will pop open. With an alveolar trill, you're just kind of trying to blow the tip of your tongue out of the way from becoming a complete stop closure. So the way I kind of think about it is if you like take a big deep breath in, open up your jaw a lot when you do that, and then like as you're about to blow out, try to raise your jaw and try to raise the tip of your tongue to that alveolar ridge and just kind of like blow out through that little closure. So you kind of like raise your tongue and jaw as you're starting to blow out, and then if you get it into the right spot without making a hard closure there, it should turn into a trill. And you can voice it if you want to. That might help. Like that. It may take some practice to be able to do that, and it will probably take even more practice to get that into a stream of speech like this, but that's the only way to do it, is to learn how to do it through practice, really, and keeping these principles in mind. Try not to like raise your tongue a bunch of times, because you can't do it fast enough to get like 25 repetitions per second, right?
Ruin,
Truin,
Rikei,
Treke,
Rili,
Trli,
Rekein,
Trakein, something like that. Also with these, like they're transcribed as pre-nasalized, but it kind of sounds like starting that off with a D. And so maybe starting this off with a D, a complete stop closure, might be a way for you to kind of easily walk into it.
Ruin,
Truin,
Rikei,
Treke, something like that. There are also uvular trills made by the back of your tongue making contact with your uvula. Those are represented with this capital R symbol, which is also a little small. So our alveolar trills are kind of this legitimate lowercase r. These are more common sounds in the world's languages than the English sound, which is why this kind of gets the default. And then the uvular trills look like the uppercase R, but again, it's not that big as an uppercase R. It's a little bit smaller. And depending on who you talk to, these are supposed to be in French. Sometimes you get uvular trills, sometimes you get uvular fricatives in French. So I've got an example here from the famous French singer Edith Piaf, who lived and performed in the early 20th century, singing her famous song. Yeah, so uvulars are a little tricky. You can hear the trilling in that, I think. By the way, what Edith was saying was, I regret nothing. And in these lectures, I have to try to regret nothing, because otherwise, yeah, sleepless nights. Anyways, you have to get the trilling with the back of your tongue. And whenever I try to do it, I find it's difficult to sort of maintain a trill as opposed to like a fricative or vice versa, which is maybe why French speakers use both. But that's the idea, is to get the back of your tongue involved rather than the front. And the big question is, we've talked about 3 different places of articulation for trills. Can you guys think of any other places for trills? Do we make them anywhere else? And since this is a question, I'm actually going to pause here for a moment and get something else set up. So you can think about it for the next 2 or 3 or 4 or 5 seconds. And then I'll come back in a second and give you the answer. Okay, hopefully you've come up with an answer by now, and maybe you can see it, what the answer is on the next slide. But often people think about things like, well, can there be palatal trills or maybe velar trills or something like that? But the answer is we do get trills somewhere else. We don't normally think about them as trills because the trills we get are glottal trills, and we normally think of them as voicing. So if you think about this sort of parallel to the way, or analogously to the way you bring your lips together when you make a bilabial trill, for a glottal trill, you bring your 2 vocal folds together. And then from underneath, you're pushing air up out of your lungs. The vocal folds are brought together lightly. They're adducted. And then you push them apart with the airflow from your lungs, right? Your vocal folds are a lot lighter, less massive. They're much thinner than your lips are. So it's a lot easier to kind of push them apart. And they're a lot more affected by the Bernoulli effect once air is flowing through them too. They can get sucked back together quite quickly and quite readily. So I'll give you an example of what this looks like. Basically, we go through the same sort of cycle. Lips, the vocal folds get pushed open, Bernoulli effect sucks them back together, and this can happen quite rapidly. I've got an example here of the slowest kind of voicing, and I've got a waveform for this as well here, so you can see kind of the individual spikes of when your vocal folds pop open and closed. And I'll play this for you. This is a type of voicing called creaky voice, which is fairly distinctive. I tend to use this a lot if you've ever listened to me lecture, and so you probably will recognize it for that reason. It sounds like that. And the reason I want to use that here as an example is because you can kind of hear the individual openings and closings of your vocal folds when you use this kind of voice quality. You can hear those individual pops. So normally, that's exactly what's happening, or almost exactly what's happening in normal voicing. But normally in what we call modal voicing, that cycle is happening so quickly that you can't hear the individual pulses as distinct from each other. So we go from this to something like this, where it just seems like smooth voicing all the way through, right? So this is called modal voicing. And again, each time your vocal folds pop open, you get one of these spikes, and they're a lot more tightly packed here in the case of modal voicing, like the type of voicing. And then the next question I have for you guys is, how fast do you think the vocal folds open and close when you're doing modal voicing or normal voicing? They're opening and closing so fast you can't hear those individual peaks in the cycle. Well, give you a second to think about an answer, but it turns out that how fast this happens depends on who you are and actually kind of how you're speaking. But there are general averages that we can get that differ between men, women, and children. So in bilabial trills, lips will open and close about 20 to 25 times a second. As we saw before, for me, is maybe a little bit faster than 25 times a second. In modal voicing, however, we get a cycle that repeats about 120 times a second for men, or 120 hertz. For female speakers, adult female speakers, their vocal folds tend to be a little shorter, a little thinner, and they open and close, therefore, more quickly, almost twice as quickly. So it's about 220 times a second for women. And for children, they're even shorter and thinner, so you get something like 300 plus times a second for children. But these are pretty reliable averages that you can get for these 3 different kinds of speakers. We'll see this as we go through. We can actually measure this pretty easily in PROT to find out how often this happens in any particular utterance of speech. These are averages again, so it can go up and below that for every single speaker, but that's normally kind of the range in which they're found. So I'll give you some specifics on kind of the numbers involved with the physics behind this, but the air coming up out of your lungs will rush through them at about 20 to 50 meters per second. And we're dealing with very small distances in the vocal tract, so we don't really need to think in terms of meters. But if you want to convert that into like a speed that we're more familiar with, like driving in a car, this would be the equivalent of somewhere between 72 and 180 kilometers per hour. Or if you're a stupid American like me and rather think in terms of miles per hour, it's 45 to 120 miles per hour. So that's pretty fast, right? Even on the low end. Due to the Bernoulli effect, when air is rushing through that quickly, the pressure between the vocal folds will be very small, hardly any pressure at all. It'll be very easy to suck those vocal folds back together, so you can do this very quickly in a short amount of time. That being said, the speed of this glottal trill cycle will depend on how long the vocal folds are, how thick they are, both of which I mentioned before, but then it will also depend on how tense they are. And this is kind of the part of this that you can manipulate most directly as a speaker. You can make the vocal folds more or less tense. And kind of the easiest way to think about that, if you've ever played a stringed instrument and you think about like tuning the instrument, like if you tighten up a string, like on a violin or a guitar, that string gets kind of tenser and like feels narrower, and it will vibrate at a higher rate. It'll give you a higher pitched sound, basically. If you loosen up slack on that string, it'll become less tense and it will vibrate at a lower pitched sound. Your vocal folds work the same way. Tighten them up, pitch goes up. Loosen them up, pitch goes down. So in men, vocal folds are about 17 to 23 millimeters long. That's not quite an inch. 25 millimeters is an inch. In women, vocal folds are slightly shorter than that, about 12 to 17 millimeters long, so maybe about half an inch on the lower end. And again, I think I mentioned this with respect to the times when we've gone into the cadaver lab for the larynx field trip with verbatim. But when you do get a view of the vocal folds in an actual human being, you find out they are small. They're like this small or even smaller, but they can make a heck of a lot of noise. And they're just kind of like these tiny little gray filaments or gray ligaments just hiding in your throat somewhere, custom designed to let the world know what you think. It's amazing. In adult male speakers, vocal folds are about 2 to 5 millimeters thick, and then adult female vocal folds are slightly thinner than that. And I mentioned this analogy before, but longer folds are going to vibrate more slowly, so you can think of like violin strings versus bass strings. That's the other kind of dimension. Just like in a violin, you have shorter strings altogether. Bass strings are very long, 4 or 5 feet long. I don't know exactly how long, but in addition to being thicker, they're longer as well. And same applies to, say, male speakers versus female speakers. Male vocal folds are going to be longer and a little bit thicker. And then I gave you that analogy too, that you can actually adjust how quickly this glottal cycle happens, how often it repeats by changing the tension of your vocal folds. That's the primary way in which we do it. With that in mind, I will give you some acoustic phonetics terminology, some of which we've already addressed. But frequency is a technical term meaning the rate at which vocal folds are opening and closing. And this is measured in hertz or cycles per second. We saw an example of how that works with the bilabial trill cycle. And sort of the counterpart to frequency is period, which is just the length of the time between cycles. So we've got this relationship. I think I wrote it up on the Microsoft Word document before as period equals 1 over frequency, but you can just flip that on its head and you get the same thing looking the other way around. So frequency equals 1 over the period. Period is like how long does it take to complete one cycle. Frequency is how many times does it happen within some time frame. Normally, when we talk about frequency, we talk about how often does something happen within 1 second. That's why we measure it in hertz. But you could also think about it in terms of a bigger time frame, like how often does this class meet per week? Well, 3 times. That's its frequency. And then in that case, what would the period be between cycles? Say if you met on Monday, Wednesday, and Friday, then normally the period would be like 2 days between class meetings. Pitch, I mentioned that term before. Technically, pitch is the perception of frequency, but normally it correlates pretty closely to frequency itself. So if somebody is speaking with a lower frequency in terms of how often their vocal folds are opening and closing, then we perceive that as a lower pitch, like ah. And then if they're speaking with a higher frequency, like ah, then we perceive that as a higher pitch. Like I said, any speaker has a range between low and high that you can manipulate as you see fit. But technically pitch is how you're actually perceiving it, not what's going on in the speaker's vocal folds themselves. Okay, we know I'm going to use this to kind of lead into another sort of comprehension question that I want to ask you guys or have you guys kind of puzzle out. But we know of two basic laryngeal settings for any pulmonic egressive sound. So first of all, we know that, if the vocal folds are adducted or brought together, and then we push air up out of the lungs, then we can make the vocal folds trill, and we can create this phenomenon of voicing. The other way to do it is to have the vocal folds abducted or held apart. So adducted, brought together, abducted, held apart. And then if you're pumping air out of the lungs as the vocal folds are abducted, then you get a voiceless sound because the air is simply going to pass through the glottis unobstructed and not make any noise other than maybe like an H. But it's not it's just voiceless. So those are two different laryngeal settings. There are two different ways to like set your vocal folds when you're pushing air out of your lungs. Stops can be therefore voiced or voiceless, and we talked a lot about different kinds of stops. But when we also talked about stops, we looked at them in terms of their place of articulation. So independent of whatever you're doing with your vocal folds, down here you can make like an alveolar stop by raising your tongue, or you can make a bilabial stop by closing your lips. You can make a velar stop by raising the back of your tongue. That's all place of articulation, and that is independent of what you're doing with your vocal folds, at least in terms of the muscles you need to use to put your articulators in those particular spots. The question I want to ask is whether these two articulatory settings are aerodynamically independent of each other. So we're doing two different kinds of gestures here. We're making a closure with our articulators above our glottis, and then we're either closing the vocal folds or opening the vocal folds to get voicing or voicelessness. So you can do those independently, no problem, with very little interaction between those two gestures. But what happens to the airflow when you do that? Is the airflow going to be independent of what is happening above the glottis or below the stop place of articulation? Another way to ask this question is, do you think it's easier to make a voiced stop or a voiceless stop? And I will let you puzzle over that while I take another swig of water. Good stuff. What do you think? What's the answer to this question? Well, I can give you some data. So this is another old cross-linguistic survey from a linguist named Merritt Rulin, who surveyed 706 different languages back in the mid-70s, kind of looking at what sort of stop inventories they had. So he found that 75% of the languages that he looked at had both voiced and voiceless stops. But out of the remaining 25%, which didn't have both pairs or both sets, 24.5%, almost all of them, had only voiceless stops. And then only 0.5% had only voiced stops. So it looks like if you have to make a choice, the more popular option is definitely just having voiceless stops rather than voiced stops. So this seems to imply that something is difficult about voiced stops. They're less preferable to having voiceless stops. What is it about voice stops that could be difficult? What is it that could possibly make us not prefer to have them in our inventory? Are they hard to produce or reproduce or understand? I'll give you some more data, which actually kind of teases apart the different kinds of voice stops we get. Are some voice stops harder than others? So I'll give you some stop inventories, which are pretty typical of languages around the world. So for example, English, we have 3 different places of articulation for stops, and we can get both voiceless and voiced stops at each place of articulation. So pa, ta, ka, and ba, da, ga, no problem. Other stop inventories have gaps. So Thai has PT and K, and it has B and D, but for some reason it doesn't have G. That one's missing. And I can think of a couple other languages I know that are like this. So Ukrainian is missing a G. Dutch is missing a G as well. That's weird. Or you can think about some other examples, like there's a language Efik, which is missing a G, and it's also missing a Pa. So it has TK, Ta, Ka, Ba, and Da. I know Arabic is missing a P as well, and in Arabic, I guess the G is not that common, but it's still there in the inventory, but it's missing a P. But it looks like when you go through these inventories, sometimes individual stops are missing. And in particular, we often get inventories that are missing a G and a Pa. So we can count that. And this is some data from a linguist named Sherman. I forgot their first name, but he found, or they found, that 2 languages were missing voiced bilabials, like buzz. 21 languages were missing voiced dentals or alveolars out of 87, and 40 were missing voiced velars. So almost half of the languages that were missing something were missing voiced velars, the g. Somehow that was bad. So it looks like voiced velars are particularly hard, or languages kind of just prefer having them in their inventories for some reason. Why is that? So before I explain one possible reason why, I will say that a lot of very clever students kind of go back to this previous point I made about voice stops being hard. And they say, well, no, I studied historical linguistics and we decided that voiceless stops are hard. And that oftentimes when a language encounters like a voiceless stop in between 2 vowels, it'll voice it. That's true. I'm not going to dispute that at all, but I'm just saying that if you have a phoneme inventory and you're missing one or the other, it turns out that over time you get this sort of pattern where languages will prefer to have voiceless stops. Not necessarily like in between 2 vowels in medial position or something like that, but they'll just have that option available in their inventory. And yeah, we have to kind of like harmonize those 2 facts with each other somehow. I'm not necessarily going to do that, but I will walk you through a potential reason why it might be hard to produce voice stops, and in particular voiced velar stops. So again, I've got some amazing artwork to try to explain this for you, but this is a diagram of the vocal tract where we have the mouth, this sort of right angle in the middle, the pharynx or throat here. We've got the glottis here, which you can open and close, and you've got the lips, which you could open and close as well at the front of the vocal tract. And we need to think about this vocal tract in terms of volume, basically, and how that relates to place of articulation. So voicing is going to occur when air flows through the glottis. So normally you bring the vocal folds together, not too tightly, push air up out of the lungs, they'll pop open, and then because of the Bernoulli effect, they'll come back closed again, and then you just kind of repeat the cycle really rapidly for a certain amount of time. So air needs to flow across the glottis to pop those vocal folds open, right? How do we get air to flow? Well, remember that anytime you have airflow, the air is going to be flowing from high pressure to lower pressure. So the air pressure below the glottis has to be higher than the air pressure above the glottis for there to be any kind of voicing. That's crucial, right? We start airflow by compressing our lungs. That increases air pressure down here. If our vocal folds are together, we're going to get voicing simply because air in a higher pressure spot is going to want to flow to a lower pressure spot, sort of above our vocal folds. That is crucial. We need that for voicing to happen on top of bringing our vocal folds together. We need that airflow. And for that airflow, we need that pressure difference. So let's say I get voicing started at my glottis, and then I close my lips. I make a stop closure at the front of my mouth. So what is going to happen here? I don't have any more water left, but I'm going to let you think about it for a second while I take a fake drink. Okay, so if you close the lips here, then all of a sudden what we have behind the lips in your mouth and your pharynx is a closed chamber of air, right? Not entirely closed because it's open through the glottis, but if you push air through the glottis from below to above, then this air has nowhere to go. It's just closed off. You're just dumping that air into like a dead end, or, pouring water through some sort of like narrow channel into a bucket or something like that. You can keep doing that for a while if there's a stop closure and air is flowing through the glottis, but eventually you're going to run out of room, as it were. Or rather, basically what will happen is that the pressure above, if you're pushing air into that spot, is going to increase, and then the pressure below will basically decrease, right? Because air is moving away from there. And if that keeps happening, something dynamic is going to occur. There's a reason we call it aerodynamics. It's a system that changes as it changes. So air pressure below the glottis will drop down here. Air pressure above the glottis will rise. And then the difference between the two is going to decrease. And if it decreases to the point where there is no difference, then voicing stops. You need more air pressure down here than above here in order to get air flowing in this direction. And just by its nature, if you keep voicing and the air here has nowhere to go, that's going to kind of kill itself off. The pressure differential will basically diminish to zero over time, and voicing will stop. So that's a little weird, but like I said, I think you can understand it by trying to do it yourself. So just try to make a B, like ba, ba, and really focus on trying to voice that B. Sometimes we just get away without voicing it. So ba, ba, and listen to your vocal folds so that you can hear that little voicing happening before you release that stop. Ba, ba. There should be a little bit of voicing that happens. And now once you kind of get the hang of that, focusing on that voicing, ba, 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 try to make the same sound, but don't release your lips. Just keep them closed. Ba, ba. You can't keep doing it forever. You can't just make like a if your mouth is closed. Voicing will stop. It will only work for a very short amount of time. So that's kind of funny. And the reason is because the air up here has nowhere to go. Like if you keep pouring water into a bucket, eventually the bucket will overflow. But if you like have a direct connection between the bucket and the source of water, eventually the water will kind of back up, right? And it'll prevent the water from flowing out of like the faucet or wherever it's coming from, right? That's what's happening here. And so you might imagine, like, if the crucial thing is that you have a closed chamber up here and that increases pressure when you pour air into it, then if you have a closure further back, that makes this chamber even smaller, and that makes this process come to a conclusion even more quickly. So the further back a stop closure is made, the less volume there is above the glottis for air to flow into. And this is trying to make it like a G. So in this case, when we get air flowing through the glottis, this pressure changes more rapidly. I've got a bigger red arrow here. And in that case, voicing is going to cease more quickly. So you can make like a G, 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 a truly voiced G. But it's hard to keep that voicing going just because of pure aerodynamic reasons. For aerodynamics to apply, you need air flowing, but if air is flowing into a closed chamber, it has nowhere to flow eventually after that. So it kind of kills itself off. So that's basically what's going on here. Hopefully it makes sense, and I will make a couple of other points about that, which is that if you do try to make a truly voiced B or G, and you really focus on that voicing, you might notice yourself making some implosives. As I was demoing that, I think you probably heard me say or make a few implosives as I went along. So B or G or D. What's happening there is that you are lowering your larynx, you're lowering your glottis to try to keep that air flowing. G, G, G. When you do that, you briefly expand the amount of space above the glottis. If you shove this down, then you keep that air flowing kind of by pushing your glottis just down on top of the air, but that keeps that pressure differential going a little bit longer. G, G, by increasing this space and decreasing this space here. And then the other thing you can do to keep that voicing going is just to make a nasal, like ba, or ga. You can keep a nasal going pretty much forever, right? Because air can flow out through your nose. It doesn't get stuck in this closed chamber of air in your mouth. It has somewhere to go. So you can keep that pressure differential across the glottis. Okay, I said, I think, enough about this, but I'll give you a few more numbers. These are from Ian Catford's Fundamental Problems in Phonetics. So he gave these stats. So like lung volume is about 1,800 to 4,500 cubic centimeters. During inhalation or exhalation, lung volume will typically change by about 500 to 1,000 cubic centimeters. So that's like maybe a quarter or a fifth of that amount of volume, which is a fair amount. But vocal tract volume, which is the space between glottis and oral closure, for bilabials, it'd be about 120 to 160 cubic centimeters. For alveolars, it's 70 to 100 cubic centimeters. And for velars, it's about 30 to 50 cubic centimeters. So that's, in each case, this is a small portion of the amount of change you get in lung volume, or how much air is coming out of your lungs. And it's a dramatically smaller portion in the case of velars than it is for bilabials. So this is basically the reason why people are avoiding voiced feelers more often than any other kind of voiced stop. Voiced stops in general will be a little bit tricky, but because you have so little room for the airflow to flow into in the case of velars, that voicing is going to be hard to maintain. So voiced stops are hard because too much air gets pushed into the mouth behind the stop closure. This makes it impossible for there to be a pressure drop across the glottis. And voiced velars are even worse because the space above the glottis behind the stop closure is even smaller, and this space gets filled up by pulmonic airflow even faster. And in each case, when that happens, voicing will stop as soon as that chamber above, the pressure in the air chamber above the glottis equalizes the pressure in the air chamber below the glottis, and voicing will stop, and you'll get a voiceless stop or just no sound. So the other kind of meta moral of the story is that you have two independent articulatory gestures. You can move your tongue independently of your vocal folds or vice versa, but they're going to have to interact aerodynamically because they have to sort of share the same stream of air in order to get a sound produced. So you can't just think about them totally separate from one another. You have to think about sort of the airflow that connects the whole system and produces a sound at the end of it. Okay, like I said, I think I've said enough about that, so I'm going to stop there. But in the next lecture, we'll look at how trilling kind of leads us into an understanding of the basics of acoustic phonetics, which we've already started on a little bit as well. So I'll look forward to seeing you then, and I'll look forward to playing with prot and computer representations of phonetics a lot more in the near future. All right.